The Global Positioning System, or GPS, is a navigation system designed to provide location data to anyone, anywhere in the world. It is a mainly space-based system consisting of somewhere between 24 and 32 satellites, depending on who you ask. There are also 5 ground-based control stations. It was developed by the United States Department of Defense, reached full operational capacity in 1995, etc., etc., but that isn't particularly relevant. What is relevant is how it works. The system is set up such that from any point on Earth, 4 satellites should always be visible, which is to say, above the horizon. The system uses UHF radio frequencies such that it penetrates the ionosphere, and each satellite transmits data indicating its location and the time at which it transmitted. They transmit other things as well, but they are really just to help the receiver know where to look for other satellites, and so won't be gone into in further depth here. So now your GPS receiver gets this information. You have a location and the time at which a satellite was at that location. Thankfully, as we also know the signal was traveling at the speed of light, we know how far we are from the satellite. Unfortunately, this is a distance, not a displacement, and so we only know where we lie on this circle surrounding the satellite. But fortunately, add in another 2 satellites and there's only one place you can be. Add a 4th, and because these are actually spheres and not circles and we're working in 3D space, you know your altitude as well. So that covers the basics, but it's actually a little more complicated than that. Because this is all based on time, the satellites need to be communicating incredibly accurate time data. And they do. But because the satellites are further from Earth, and hence affected by different strengths of gravity, and are moving relative to Earth, both general and special relativity, respectively, come into effect. This is really quite complicated, and while I may almost understand the concept, of special relativity at least, I won't even pretend to understand the math. Basically though, the faster you're moving, the slower time passes, and the further you are from a gravitating body, the faster time passes. As the name suggests, these are both relative, and the satellites know their position, and hence gravitational differential, and how fast they're going, compared to us on Earth, they can do some rather ridiculous math, and work out how to compensate. So, that's how it works, but what is there in terms of current research? Well, there doesn't appear to be much in terms of research in improving the core concept of GPS technology, but there is still some interesting development. There's new satellites. As the satellites are only designed to last 10 years, and new technology for making better ones constantly becomes available, GPS satellites are often being replaced. The next generation, to begin launching in 2017, is called Block 3A. The 2 general improvements it will introduce are a dataless acquisition aid and forward error correction, each of which I will go into more detail later on. There are also new applications of GPS, and I will go into a use of the technology that you may not have thought of before. And I'll talk briefly about an alternate positioning technology. While what I will go into there is not technically part of GPS, it was still interesting and was in fact the first result when I googled current research in GPS technology development. So let's start at the start of that list, with the new satellites. Block 3A is the 7th generation of GPS satellites. Generally, each generation makes basic improvements on the last, for example, in the material makeup of the satellites, but as I mentioned before, there are 2 general improvements which this generation is looking to add to GPS technology. The first is the dataless acquisition aid, which is basically just a signal which is easier to pick up and recognize because it contains no data than the signal that does contain data, this is, and it helps the receiver to know where and how to look for the actual data transmission. Forward error correction is, for me at least, much more exciting. Forward error correction is the idea that the receiver in an information system can correct the errors in the transmission. It is useful where either the system is one way, or it would take a long time to get a response from an inquiry as to the erroneous nature of the information received. As GPS is one way, and there is, relative to the speed at which the devices using it operate, a reasonably large lag between the transmissions, forward error correction will be very useful. It works on the principle that there will generally be less noise, which is to say interference, than there will be actual data. A simple example of forward error correction is to send all the data 3 times. This way, the receiver simply takes the most common bit and uses that. In practice, of course, it is quite a bit more complicated, and often not this inefficient. One example of future applications of GPS is in space travel itself. It is completely valid to use GPS to locate yourself in 3 dimensions in space, even further from Earth than the satellites are. All you need to do is be able to receive data from at least 4 satellites, know what the time is, and perhaps do more calculations accounting for special and general relativity due to new velocity and gravitational differences. And due to the fact that, according to a NASA article from last year, 60% of the predicted launches in the next 20 years are expected to be in low Earth orbit, and 95 at or below geosynchronous orbit, it would make sense for these projects to use GPS positioning data. And finally, that other idea about positioning systems that I mentioned that came up when I googled current research in GPS technology development. The particular idea that I would talk about is visual navigation, basically just what people do. We can look at a place that we are familiar with and instantly know where we are. That sounds simple, but it's not as easy for a computer to do. Basically though, the idea is quite simple. You tell the computer where it is, for example, my room, my room. It then looks around and takes notes of what is there, and remembers it. Then it just keeps checking for those things. Once it can't see them anymore, it realizes it has moved, and checks for new things to remember. The next time it sees any of these things, it thinks, oh, perhaps I'm there again. This is all part of the developing situational awareness of computers, which many tech companies want to see become mainstream, and it will be integral in many augmented reality systems. But that is not really what we're here to talk about. This kind of system is different to conventional GPS systems. It is designed to be standalone, such that a single unit can work when it's on its own, even in locations without satellite reception, whereas GPS requires 30-something satellites in 5 base stations around the world. However, visual navigation technologies cannot currently tell the difference between 2 streets that look similar, and give you no indication as to your actual position on the planet. So perhaps they serve different purposes, or perhaps a combination of the two would be desirable. So that was a bit of a tangent, but I hope that overall I've aided your understanding of GPS. So thanks for watching, listening, or otherwise consuming this information. And good luck, just kind of with everything, generally. Now this does raise a few questions that I haven't gone into here. For example, how the satellites know where they are, and how the hell general relativity works. But perhaps that's for another day.